we created the finite element mesh from the toolpath, which is a unique feature of Aibuild. We don't do it from the CAD file, CAD and the mesh, two different things, and so is the toolpath. We've got information on interpass temperatures, what layers are out of bounds. We have the finite element simulation itself, which is always the part that people like to see. The simulation here is in real time as well, but we can use that simulation to optimize our toolpath automatically. You see now every single layer has been given its own interlayer dwell period. So you can see for the first few layers, there's no pausing necessary, but then the heat starts to build up. It goes above our maximum threshold temperature. You get accurate production time estimations as well, because the printing without the pausing, just straight printing, is about 15 hours. When you add the pauses in between the layers, we've nearly doubled the print time. Yeah. So that's important for production planning and time estimation. And this one as well, I also took the liberty of creating a finite element analysis. So we created the finite element mesh from the toolpath, which is a unique feature of Aibuild. We don't do it from the CAD file, the CAD and the mesh, two different things, and so is the toolpath. And
which is actually what should be analyzed.
Yeah, exactly. You know, if we analyze the CAD file, it will show us one thing, but really we are weaving the whole part, right? We've got a strategy that's pretty different to the CAD file. And then if we go to our thermal analysis, see this one took about a day. So for a high resolution thermal simulation, not too bad at all. We've got information on interpass temperatures, what layers are out of bounds. We have the finite element simulation itself, which is always the part that people like to see. So we'll just speed this up. But it's the simulation here is in real time as well. So we can see the weave pattern being printed kind of element by element. We could be here for a good 15 hours watching this if we wanted to. But the important thing is once we've created our simulation and performed it, it give us information, like I said, interpass temperatures, out of bound regions. But we can use that simulation to optimize our toolpath automatically. So here I have my toolpath. And if I go to pre-weight layer time, you see now every single layer has been given its own interlayer dwell period in order to manage.
According to the thermal analysis.
Yes, exactly. It uses a thermal analysis to give each layer a bespoke dwell period. So you can see for the first few layers, there's no pausing necessary, but then the heat starts to build up. It goes above our maximum threshold temperature. So we have to pause, and we have to pause gradually more and more, and a little bit less as the heat input's less. Then here we have quite a bit more as it becomes like a smaller region. There's the base plate is down here, which is absorbing heat in the early layers, not so much here. So this is really helpful for, well, obviously controlling thermal management, make sure you don't overheat. You can control your mechanical properties a lot more by controlling the cooling and the kind of interpass temperatures. You get accurate production time estimations as well, because the printing without the pausing, just straight printing, is about 15 hours. When you add the pauses in between the layers, we've nearly doubled the print time. Yeah. So that's important for production planning and time estimation. So that's also had some general improvements.
We've have to make it by hand without the analysis.
Yeah, exactly.
And there was a new feature in the finite element about measuring temperature.
Yes. Yeah, when we're in the simulation itself, we can click on different points on the mesh as it's running, just to see what the temperature is at that moment in time. So here at the very beginning, I have a room temperature of 20 degrees. So that's what we're reading, is 20 degrees. And then as we deposit, this will all start to heat up. So let me skip ahead so we can see a bit more. Obviously it's quite a, there we go. So that's nice. You can see the differences in heat buildup across the part. We have a lot more material over here, so it's a lot warmer than it is over here. So if I click on this point, I can see that is at this time moment 515 degrees. Over on this end, it's much cooler at around 210.
Yeah.
And obviously the base plate has that nice variation in temperature. And the next step for this year is to have a thermal mechanical simulation as well. So that's going to be huge. We're talking analyzing the internal stresses, distortion, warpage. Part like this with such a varied temperature gradient across the part, we're going to have quite a bit of distortion and warpage. And that simulation will show that with the same kind of mentality in the feature to use the simulation to automatically optimize the toolpath. Whatever that may be, it can provide information how much clamping force you need, maybe changing directions on different layers to cancel out stresses, change heat inputs, possibly even pre-distorting the part so that it warps into place if that's relevant. If this part here is going to start bending to the right, for example, then we can kind of print it the opposite way. So yeah, lots of different things that we can think about doing. I'm sure we'll have more to show on that in the next couple of months as well.
Yeah, thermomechanical. I'm very excited about that because we're one step closer to closing the loop. So everything goes into the right direction now.
Yeah, it's going to be the golden egg, I think, of DED is being able to simulate and optimize your toolpath, and doing that for thermomechanical is a really big deal. So super excited for that.